In the last lesson, we discussed that the first derivative test is for finding local extremes, local max, local mins of the function f of x. In this lesson, we are going to discuss the second derivative test, the concavity test, and the point of inflection test. All three of these involve the second derivative. First, let's take a look at what is meant by concavity. Consider this function here, which I will label f of x. Notice that there seems to be a cave, and this cave is facing down. Notice that the vertex is up, but the cave is facing down, and because the cave is facing down, we call this graph concave down. Essentially, at every point on this curve, we would say it is concave down at that point. Now, some functions are less obvious in their concavity. For instance, take a look at this one. Even though that doesn't look like the traditional cave, we would still say that it is concave down in appearance. If we look at these functions, notice that the cave is facing up. Again, that means at each point along the curve, if we call this f of x, the curve's cave is facing up. Again, and in the less obvious case, here at all points the curve is facing up, so we call these concave up. The idea of concavity is a fairly simple one. This could be illustrated to someone perhaps in 7th grade, just asking them, where is it cave up, where is it cave down? So the visualization is a very simple process, but what we're going to do in this lesson is look at the calculus to describe these different features, such as concavity. Now, before we do the concavity test, let's take a look at the visual of something called a point of inflection. Scroll down so we can take a look at that. Let's take a look at this function f of x. You will notice for many points the function is concave up. So as I trace here in orange, it's concave up, concave up, concave up, concave up, concave up, concave up. And then at some point it appears that it switches concavity. Now it's concave down, concave down, concave down, concave down, concave down, concave down. And so a point of inflection is that very point where the function changes concavity. In this second function, which resembles a bell shape, we will see here that it's concave up, concave up, concave up, concave up, concave up, and then again at some point it changes its concavity. So in this interior part, it's concave down. Remember, the cave is facing down even though the vertex is up. And then it switches back to concave up, concave up, concave up. So this graph here has 2 points of inflection, there and there. So a point of inflection is f has a point of inflection when f of x changes concavity. And now we have 2 tests that will require calculus to determine intervals of concavity or determine points of inflection. Okay, we will do the concavity test first. In order to do that, we should investigate a couple of these concave down graphs, or we can look at the concave up graphs. In fact, let's take a look at the concave up graph. If we look at the slope here, the first derivative, now that's a horrible tangent, but that's supposed to be a tangent line. If I look at that tangent line, we see that it's a negative slope, and let's just say negative 200. And then I'll move from left to right at a different point, and then that slope is maybe negative 20, and then negative 1. At some point we see we have a horizontal tangent, so the slope is 0, and then it's 15, and then it's 45, and then it's 300. So you can see that those slopes are increasing. Same thing here. Slope is 1, slope is 10, slope is 45, slope is 262. The slopes are increasing. Last class we remember that f increasing goes with f prime greater than 0. But now I want to say f prime is increasing for concave up, which will go with f double prime positive. Now let's put this in form of a sentence. F is concave up on, the good news here is we always use parentheses, and I'm just going to make a generic interval a to b, and the reason is because, and it's because f double prime of x is greater than 0. In other words, f prime of x is increasing. We typically don't need both of these, but for the notes, it's important that we see the connection. So f is concave up on open AB because f double prime of x is greater than 0 on this interval. Similarly, we wrote the sentence for concave down. F is concave down on open AB because f double prime is less than 0. F prime is decreasing on this interval. And now for the point of inflection test, remember that's where the function changes its concavity, and that's going to occur when the second derivative changes sign. So we will say f has a point of inflection at x equals, and I'll just make up a generic number c, at x equals c, and that's because f double prime of x changes sign at x equals c, at this x value. Some people mistakenly say it's because f double prime of x equals 0. That is an important quality of this. We will find where f double prime equals 0, but we have to ensure that the second derivative changes sign in order for there to be a point of inflection. So this is important, but it is not the justification. This here is the justification. Now, if we scroll back up to the top, the concavity test is for finding intervals of concavity. And the point of inflection test is for finding, you guessed it, points of inflection of f of x. Now we get to this pesky second derivative test, and we wonder what that's used for finding. Again, the first derivative test was for finding local extremes of f of x. The concavity test for finding concavity, point of inflection test for finding point of inflection. The second derivative test, though, what does it test for? Well, the big reveal. It's for finding local extremes of f of x. What the heck? These are used for finding the same exact thing. So whether we're using the first derivative test or we're using the second derivative test, both of these tests are used to find the same exact thing, which is the local extremes of f of x. They are different methods to find the same thing. Let's scroll to the bottom of the page to develop this theory further. Here's the idea of the second derivative test. I'm going to draw a curve with two humps like this, and it is clear to the fourth grader that this thing has a local max at this upper vertex, and this thing has a local minimum at this lower vertex. Okay, so what's happening at those vertices? Well, we see that we have a horizontal tangent for both. Horizontal tangent there, a horizontal tangent there. I'm going to go ahead and draw the x-axis beneath it, and we'll label where this thing occurs at the upper vertex. We're going to say that's x equals c1, and at this downward vertice, we're going to call that at x equals c2. So I can see here that f prime of c1 equals 0, and I can also see here that f prime of c2 equals 0. So that's a common characteristic of both the first and the second derivative test. We have to find these critical points. We have to find the values of x where we have horizontal tangents. So now here's where they differ. See, in the maximum curve over here, we have a horizontal tangent, so that's good and makes it a vertice, but you'll notice at this singular point, this thing is going to be concave downward. So we have a connection. F prime of C1 is equal to 0, but at that very point, we say, and F double prime of C1 is going to be less than 0. Now take this in. Because the second derivative is less than 0, it makes the cave down, but that makes the vertex up. And so therefore, F has a local max at x equals C1. This confuses some people because they think the second derivative negative, how can that associate with max? Remember, negative, concave down, but makes the vertex up. That's why we get to the max. Down beneath here, f prime of C2 equals 0, and at the same time, the second derivative at C2 is going to be greater than 0. We know that because we see concave up. So concave up, vertex down. And therefore, F has a local minimum at x equals C2. That's the idea of the second derivative test.